Welcome back to Seacoast High School's remote trigonometry class. My name is Eric Fearing. I use he, him pronouns, and most of my students just call me Mr. Today we are going to work on the real meat of the triangles competency. We are on to benchmark 7. Those of you who are following along may notice we skipped benchmark 6 because we're not going to bother with it during our remote learning closure due to COVID-19. Benchmark 7 is to use the sine, cosine, and tangent functions to solve for missing sides in right triangles. So I created this diagram which references back to my video on the Pythagorean theorem, where we took an equilateral triangle with 3 sides the same and split it down the middle to find the lengths of the 3 sides. So we've seen this diagram of a equilateral triangle cut in the middle before, and I want to point out that because we did it that way, we know that it's a 30, 60, 90 triangle, oriented like the one over here. So the usefulness of the trigonometric ratios isn't just in being able to write them and recognize them. It's because triangles that have the same angles are similar, and that means that they're going to have the same ratio because their sides are going to be all in proportion to each other. For example, the smallest triangle we have here is marked in red. Angle theta is the bottom left-hand corner of this. It's the 60-degree angle in this 30, 60, 90 triangle. If we want to write the cosine of theta, like we've done many times before, we would take the adjacent leg and divide it by the hypotenuse, just because that's the definition of cosine. The adjacent is 1/2, the hypotenuse is 1, which gives us a cosine of 1/2. If we blew that up and created a larger triangle of the same proportions, double the width, we're going to double the length of the hypotenuse, we're going to double the height as well, we'll know that the base here is 1, and that the hypotenuse is 2. It's half of a side 2 equilateral triangle. Still has a 60-degree angle. So the cosine of angle theta in the green triangle, we could solve by saying, oh, well, the adjacent leg is 1, and the hypotenuse is 2. So the cosine is 1/2. That ratio stays the same as we make it bigger. Because we know it's a similar triangle, we know these proportions are going to hold no matter how we scale it up or down. If we go and look at the biggest triangle I have drawn here, it's going to have a base that runs all the way over to here and is approximately 2 units long. It's about the same as the previous hypotenuse because I'm just an excellent artist. Then how long is its hypotenuse? Well, we doubled the base, so we should also be doubling all of the other sides. This 2 would expand to be 4 units long on that diagonal, the hypotenuse of the triangle. So if we wrote the cosine for theta according to the blue triangle, we would have a ratio of 2 to 4, adjacent leg along the base and hypotenuse 4, which reduces, surprising hopefully no one, to 1/2. So the cosine of 60 degrees is always going to be 1/2, or if you go to a calculator and ask it the cosine of 60, it's going to tell you 0.5. That gives us enough information to solve for a missing hypotenuse or adjacent leg to a 60-degree angle in any triangle, well, any right triangle anyway, by just writing an equation based on one of the definitions of a trigonometric function. If we know the angle, then we can look up its sine, its cosine, or its tangent, because graduate mathematics students have been doing that and creating these giant tables for hundreds of years, and now we've stored them in calculators and on the internet. So if we know an angle, we know the sine, cosine, and tangent. As long as we know one side, the opposite, the adjacent, or the hypotenuse, we can find either of the other sides by selecting the correct trigonometric function. we're going to do this a handful of times because this is going to be probably a bit of a time-consuming task for you as you get to the homework problems. So, back to that. We're being asked to find missing side lengths. So I'm going to sketch my first triangle, which is off an alternate version of the posted problem set. It has a right angle at the peak, a 62-degree angle here, and a base of 13, x on that side. So I'm going to label it the same way. Angle AB, triangle ABC. We want to find x. Okay. We know the 90-degree angle. We know the 62-degree angle. We could figure out what the third angle is, but we don't necessarily have to. Let's just use what information is here and figure out whether we should apply the sine, the cosine, or the tangent to it by labeling our sides according to this angle. So the hypotenuse is 13. Easy fact. B is 62. Across from that is x. This is the opposite side. All right. Obviously, the third side is the adjacent leg. We're already here. We know enough. Which of the trigonometric functions are we going to use? We know the opposite and the hypotenuse, so we're going to use the sine function. The sine of 62 degrees is opposite side x divided by hypotenuse 13. What is the sine of 62 degrees? I don't know off the top of my head, but I can certainly go and get that from a calculator. I'm going to desmos.com/scientific to make use of their calculator there. Make sure it's in degree mode. It should say DEG in this box right here. If you click it, it switches to radians. We do not want that right now because we're measuring angles in degrees. Radians is in competency 2. So to find the sine of 62 degrees, I click sine and I type 62, and there we have it. It's 0.8829. 0.8829 is our pretty detailed approximation. So now I've got that equals x over 13. To solve for x, we need to multiply both sides by the denominator. And multiply by 13, I'm going to do on my calculator. Any old calculator will do that one for us. And I'm going to round my final answer here, x, off to 1 decimal place, 11.5. Now I want to think about whether that makes sense in the sketch. It's drawn roughly to scale, like this looks like about a 60-degree angle. So if this is 13, then I should have a fairly long leg. 11.5 seems perfectly fine. So that was a time when we knew the hypotenuse and we wanted to find the opposite. So we used the sine function. If we knew a different side or wanted to find a different side, we might use a different function. So now I'm going to take triangle ABC a little differently. We're going to give it a 69-degree angle at the peak, a base of 9.9 units, and we're going to try to find the height, x, the length of AC. So here's the hypotenuse. That's not information I have, and it's not information I want. I don't have a label for it as a variable or as a number. So, all right, not helpful. That should already make you think, oh, I can't use the sine or the cosine because those have hypotenuse in them. We're going to have to use the tangent. The tangent ratio is the opposite divided by the adjacent leg. So we're going to write our equation. The tangent of 69 degrees equals 9.9 divided by x. And we can solve this by multiplying by the denominator x right? So x tangent 69 degrees equals 9.9. I know the tangent of 69 degrees is just going to be some decimal. I'd rather write the tangent of 69 degrees right now because I know it's exact, and I know that decimal is going to be huge. I will just divide by that tangent. I know it's a number, I'll find it in a moment. Tangent of 69 degrees. And so I've solved for x as 9.9 over whatever the tangent of 69 is. You definitely need a calculator to find the tangent of 69 degrees. So we're going back over to Desmos. And we can type this in as one expression if we want. 9.9 divided by the tangent of 69. Make sure you're in degree mode. And there you have it. If we hit enter, it'll move it up top for us. X is, I should probably say approximately, since I'm going to round it off to 3.8. Let's do one more. Let's think about another triangle with a right angle peak, sides of 9, unknown hypotenuse x. We'll label this. Angle B is 32 degrees. So if we want to find x, and we know 9, and right now it's easiest to see the angle B is 32 degrees, we're going to label our sides in relation to the angle we know. X is the hypotenuse across from C. 9 is the opposite side. So adjacent is the one we don't know. Don't need to know that. The opposite over the hypotenuse is the sine. So I can write my equation. The sine of 32 degrees equals 9 over x. We have x in the denominator again. So I'll multiply by x. 9 is x times the sine of 32. And I'll divide by the trig function. X is 9 over the sine of 32 degrees. Go to the calculator. 9 divided by the sine, this time, of 32 degrees gives us, x is approximately, because we're rounding off, 17.0 to 1 decimal place. So those are some examples that match up with our 7th benchmark, using the sine, the cosine, and the tangent functions to solve for a missing side in a right triangle. Thanks for sticking with me, and good luck on the practice. If you need to get in touch, you can use Google Classroom, Google Voice, text messages are fine, or come to office hours on Zoom Tuesdays and Thursdays, 1 o'clock to 2:30. Thank you and good luck.